and we will be back with Francesco Borrelli's talk. Thank you.
I usually play with the controller. In real time, that's what all this field here is familiar with. You need an optimizer to solve for the best policy parameters, given all the constraints and the model you design offline. In general, you also need an observer because this model is a state feedback model, so you need something that allows you to go from output Y to a state, and then once you have solved the optimization problem, your policy, you have your control input. In learning MPC, what you do, you get, in one version, you get rid of terminal cost and terminal set, and you use input-output. You introduce this additional block in the middle, where you use input-output data to update some parameters of that parameterized virtually your terminal cost and terminal set. Okay, that's what I'm going to call learning MPC. In general, since you're doing a learning and update, you can also update your parameterized model. Melanie get great results with Gaussian process, for instance. It would be parameters. You can use a neural network, and this would be an update of your parameter here. Okay. So real time is still the same story. You're going to use your favorite solver here. I have to try a pulse solver, and at this time will be for a given parameter. You will get an optimal policy. Okay. Now we go to reinforcement learning. You see what as I go through this class, the design, things will disappear. This part of the gray box becomes smaller and smaller. Okay, now I get rid of the constraints. I put that in the cost function. In general, the poly class is a neural network. Model usually comes from a simulator, and the cost is often over one step. So you don't even need to tune the horizon end. Get rid of constraints. Very simple to design. The learning becomes heavy. The learning becomes heavy because what you do now, you learn the policy parameters, try to offline, using input.data, okay? And sometimes you do this with a value iteration or a policy value iteration, and this optimizer is some form of stochastic gradient descent. A lot of the time it's just a smart enumeration because you have a one-step optimization. In real time, it's easy. You just need a function evaluation. Okay, it's an output-input policy. It's called end-to-end. You go from images to input, and again, the evaluation is pretty simple. So you moved all the computation to the learning stage. One more step where almost everything disappears. That's imitation learning and behavioral cloning. You just pick the policy class and you try to smartly design your experiments so you have a good training set of input-output sequences. Okay, and model has disappeared, cost has disappeared, constraint has disappeared. You can imagine if you are not. Why this is appealing for a young generation, right? I don't have to do anything at the design stage. I run a lot of experiments in a smart way, and in real time, I basically need, in offline, what I do? I need to regress, I need to find the policy parameter that best fits the data that I've collected. Real time, again, is very easy. It's just a simple function evaluation, okay? So as I go down from MPC to learning MPC to RL to imitation learning, what happens, what you see is that you have an increase of use of data and a reduced use of design, okay, of design elements. The increased use of learning, and in particular, because learning becomes heavy, learning shifts from real-time heavy to offline design heavy. Right? This means that, for instance, if you're doing a policy update, you could do a policy update in real time with a learning MPC. It becomes harder to do in milliseconds with the reinforcement learning, and even harder with imitation learning. That might take days to train this policy, right? Some reinforcement learning some paradigm here, they also require heavy storage. This neural network might be large. There is actually a subclass of this. There are recent papers in our field that use actually ChatGPT to get input to output data. Here is my camera's images, here are my time sequence. Tell me what angle should I send to my dog to control. There are papers that just have been published in this field, and they belong to this class. So where are we using these techniques and how we are combining them? I'm going to focus only on cars. I've been looking at cars for many years. And these are the cars we play with in my lab. Internal combustion engine, hybrid engine, electric engines, big cars. This is an autonomous off-road vehicle. It's used for doing autonomous solar constructions. Those are open source projects. It's a race, a little 1 to 10 scale car. It's a new vehicle we are building for the Navy, which is a skid steering. It doesn't have an Ackerman steering, where you can 4 independent wheels. We'll post the design. They're all 3D printed. They don't cost more than $500. So why it's interesting? Because I'll show you can build a number of cool control problems for just one or a few vehicles. The modeling belongs to 2 classes. One is you model the energy conversion. How you go from a source of energy to wheel motion. Okay, and this really depends if you have an internal combustion engine, a hybrid, or an electric vehicle. The second part is about the motion of the vehicle. Now that the wheel moves, how does this translate into vehicle motion? There are 3 components. First is kinematic. What is kinematically feasible given your steering, given your wheelbase? If you are here, there's sinus and cosinus. These are non-holonomic constraints, right? You can also use, if you use inertial frame A would be a local frame with respect to a given path. Then dynamic. Then you need to think about what is dynamically feasible when you start accelerating. What are the forces, how the vehicle moves? That's where you have Newton-Euler equations. Linear, if it's longitudinal, bilinear terms if you start having rotations and so on. Finally, what is the interaction between the ground and the wheels? And these are very complex, and this is really where the highest part, the uncertainty comes in. And otherwise, these models are all well known. There are entire conferences on cars. You can even entire conferences on tires. Okay? And a classical model, everybody is called the magic formula, as this piecewise linear behavior that's saturated and then it goes down. So if you learn control theory, the first example I teach you is cruise control. Okay, everybody knows cruise control. It's probably, they also give it for free in a car. Very few people use it. It senses your speed and try to control it to a reference speed, a given speed that you can change on your steering wheel usually, by changing some actuators. If you have an internal combustion engine, you change your throttle because this changes the intake of airflow, which changes the power, which changes the torque to the wheels. Okay? In an electric vehicle, it will be different. What is cruise control in 2024? Cars are smart, they talk to each other, they can make micro platoon, they talk to infrastructure, and they decide what is the best reference for themselves so that the platoon moves smoothly through the intersection. This is a sequence of traffic lights, so that you maximize throughput, you want to get home faster, and minimize energy efficiency. Right? So that's, if you think about it here, everything is well known. Models of powertrains are well known. You have hard constraints. You don't want to bump into other cars. Really, the learning part of here is this use of data for learning traffic patterns and traffic light patterns. Okay, so becoming red or green and so on. Okay, this is really what learning means in this simple scenario. And without reading all the points here, what we do with MPC at many, many levels. Okay, so at the higher level, there is speed reference planning. You have statistics of traffic lights. That's a mixed integer quadratic program, which you solve with some heuristics. Then the platoon talks to each other, it controls the speed of the platoon. With hard constraints, you don't bump into others. Then you have to control your own acceleration, and then that acceleration is to be converted into powertrain, and there you have another optimization where you have to decide do I switch electric versus internal combustion engine, right? This is not made, people ask me if I made this with some AI. This is a recorded video with a drone, and these are students in the cars. It's South Los Angeles. The 3 cars are talking to each other, talking to this traffic light. It's all what I told you is happening. They will see that when the traffic light turns green, they move at the same time, but versus there is a big gap with the human-driven car, probably is looking at the phone. The interesting problem you might appreciate that there are at least 3 levels of optimization, and QP is running in real time, and this is totally feasible. Learning here using classical MPC, where you update cost functions, it just works and it's simple. Okay. Let me make the problem a bit more complex. I just want to control now steering and acceleration, lateral motion, and I want to go at high speed. Before it was low speed and longitudinal. I want to go at, and the simplest problem in this class is basically learning to race by yourself. There's no other driver around you. So I want to control steering acceleration, but I don't know what is the minimum time path, and I don't know to stay along that minimum time. So it's path planning as well as path following. So what is unknown here is really, as I told you before, the tire forces. Okay? And so what do? We use learning MPC. We collect data during experiments, and we update the unknown tire forces as well as the feasible set and the cost to go. Okay? What I've seen, remember the picture before? I put everything in blue because now the learning is not at the design stage. This happens in real time as I collect the data. And the tools I've used are super simple. I love simple tools. From a modeling point of view, we do local linear regression. Local means local in space, in a given part of the racetrack. Okay? From a target set, you accumulate data, take the convex hull of everything. Okay? And put that as a terminal set to reach the end of your horizon. As a terminal cost, it's a barycentric approximation. Take all your data and take the tightest piecewise linear convex lower bound. Okay, it's very easy to build. Think about it. In fact, you don't have to build it. You just need to write it as an auxiliary variable in your optimization problem. So the theory tells you if you use these three very simple techniques, you actually have constraint guarantees if you trust your model. You also what will happen is every time you update the cost to go, performance will decrease. That's what the theory tells you. And in practice, this is what happens. It is pretty beautiful because in practice, the forces are unknown. There's all powertrain dynamics that we have not modeled. You see the lap time on the x-axis, on the y-axis, and the lap. At each lap, you update the cost and safe set. And constraints are guaranteed, meaning the people driving this car don't go outside. And this car is it's very unsafe to run at high speed on these vehicles. Okay. Performance improves. You go to 100 to 40, okay, it's more a 2x factor. And it's data efficient, meaning I'm not generating data from a simulator. I'm taking my Newton's law and I'm testing on a car. Nothing else, okay? I don't have any web scraping of any videos going on here. This is when it's learned, lap 20. When you hit the wheels quickly, it means that you're at the peak of the tire forces, right? If you love with car, you see that it's reaching the apex. This is called the apex of a curve, and he has found this path. We could look at this for hours. The vehicle has found this path after running 10 laps. I didn't tell the vehicle what was the fastest line to follow. Okay. One more step. I'll make it more difficult. In this racing, I had differential GPS. There was a base station, I know exactly the state of the vehicle. I want to race only with camera images. Now I go to the little car because that feels unsafe to me. And what we do, I don't know the full set. I just want to close look with images. Okay. So the classical approach today, especially if you belong to a computer science world, avoids LAMP simultaneously the observer, the one that tells you where you are, plus NPC, and just do imitation learning approach. Here's what we use. On the top, here's a neural network. Again, this neural network is trained by using, this neural network parameters, okay, is trained by using expert NPC. So it's an NPC that is generating data to race this car. However, the NPC has full set information versus the network is only trained based on images, corresponding to the state that NPC was using. So at the end, you're going to have a full network. That's a classical approach using in this imitation learning. At the end, the data is generated using full state and images, but the network to evaluate in real time only needs images and inertial measurements. Okay, so we have been playing for a year, and this thing doesn't really work well. There's a lot of crashes. We can make it work at low speed, but still, I think we're close to give up. It's extremely hard to make this work at very high speed. There's a star note here. There are people having amazing results with behavioral cloning, with drones flying at high speed, and dogs. I do not know yet why, if there's something we're doing wrong, or it's a different class of application. That would be an interesting question to figure it out. Let's go to low speed again and increase the number of vehicles. Okay, so this is a good, if you teach control, this would be a good example for your class. The vehicle, so kinematics are well known. This is sinus and cosinus. Vehicle 3 wants to take the spot of vehicle 0. Vehicle 1 wants to take the spot of vehicle 2. 2 wants to go to the left. 0 wants to go to the right, but 0 is parked upwards, so he has to back up and go here, right? So Shu came up with this problem. And you know, the interesting thing about it, if you try to solve an optimization problem in any form you won't be able to solve this. Okay? MPC, reinforcement learning don't work. There is code online, you can try, I'll be happy to, if you prove me wrong. It's just too complex. You have 12 states, you have 6 states times 4 for each vehicle, a very tight non-convex space, which changes as the other vehicles move, right? So what do we do here? We do RL plus MPC. The RL part uses a checkboard model where the squares are the initial conditions, the dark versus lighter means the orientation, okay? The circles are the end conditions, and basically using a simulator to figure out what the strategy is. Should I back up? Should I go left? Should I go right? Okay. The RL then is not implemented, generates constraint to fit to an MPC, which then generates kinematically feasible trajectories. That is at this point, I believe, is one of cleanest, and you can think of this being as a way to avoid mixed integer optimization, which is very hard, by using a simulator. Okay? In this specific case, actually, you could probably try to formulate this with an MIFP. Here is it's very hard to look at 2 videos at the same time, but this is the policy learned with RL that gives the constraints to the MPC, which computes the path in moving horizon, okay? So probably if you fix to the left, I'll play it again, you can see the strategies, try to back up, and if you move to the right, if you look, let me see if I can play the game, you'll see the 4 vehicles, okay, doing this coordinated motion of that brings them to the end point. Okay. Let me conclude with one big problem, one of the hardest problems for self-driving cars today. If you have a signalized intersections which is not, if you have a complex intersection which is not signalized, you are the red car. You have bikers, you have pedestrians, and their predictions are multimodal. This vehicle could go straight, but there is also a probability it can go right. And not only if my action will change the plan of the other players around me. This is an extremely hard problem. There's not a clean solution today how to solve this. Okay, you really hope that the intersection is signalized and that they respect the rules. Okay, which is not always the case. Okay, so summarize. I want to give you an overview of the class of problem we solve in the lab. We start from something that is simple, where classical MPC works, even if it's actually complex in terms of all the pieces you have to compose and put together. Something where LMPC is suitable, because you have hard constraints, and I don't have a simulator, okay? And you're having people that drive these vehicles at high speed. To reinforcement learning behavior of cloning, where you still have where it's okay if you can fail, like the little car, and you can collect a lot of data, okay? To problems where you can cleverly merge RL and MPC seems to be a good idea. To problems today you cannot solve. Well, and the LMPC people say, well, if I can forecast multimodality and Paul gives me a faster solver, if computer become faster, then one day I'll be able to do this. That's one view of the world. The other view of the world is if I collect enough data and the past is like the future is like the past, then you would be able to solve this. And it looks like this is where we are landing. There's really nothing almost in the middle. I'll switch now to questions here. If it feels like it's a disconnect between the two parts, there is, it was done on purpose. The second part is on powertrain. I'm going to, so far it was about controlling steering and acceleration. I'll tell you about the work I've been doing on trying to learn the energy part of it, okay? And which brings me really to the title of the talk. No questions? Okay. So here's what I've been thinking of for the past 5 years. It's how hierarchical control is pieced together when you make a mission for electric or capacity constrained vehicle. What you see to the left-hand side is the schema for controlling a fleet of electric buses. At the bottom level, you have the drivers that do daily tasks. They drive, they trips, they stops, and they also have to decide when to charge, for how long to charge, and where to charge this bus. These are battery electric vehicles. Okay? And the top level, you have a monthly planning of these buses, of the work that has to be done by each bus. A block is a piece of work that has to be done every day. That's the notation they use. And usually this is done in a centralized way by looking at the demand of the community, by maintenance and so on. And then you have these two layers in the middle where you change your block for a day for each bus, depending on weekly first and then daily later, depending on many factors, including driver availability, charge availability, bus breaks, and so on. If you think about this, while talking to yes.
So it's not necessarily transit, right? I mean, public transit, or it is not public transit?
In this case, this example is public transit. Public transit. That's good. So, 4 years ago, I was talking to Alessandro Pinto at JPL, and he has a new. Is in charge of trying to make safe missions in exploring planets, and this is the planet they have for vehicles on Mars. Okay, it's striking similarity in terms of division of time. At the lower level, you have these rovers. They go and execute tasks. They move from A to B. They drill. They move to another place. They take pictures. And the higher level, you have this strategic planning. 30, 60. These are sols are Martian days. I think a bit longer than daily days. Earth days, sorry. And then you have this supra-tactical, that's their language. Supra-tactical, it's a week, and tactical is a day or 3 days, right? So, very interesting. That's when we decided to come together and think about there was something interesting to study here with Bartolomeo. So, the goal is really to think about, as fleets are electrified, this is transit, this is our off-road drones, these are sail drones used by the Navy, they're all battery electric vehicles. You really need coordination of high-level, energy-aware task planning. Can I do this task? Do I have enough energy to come back and charge? With low-level predictive control that does the planning. That's really the underlying motivation of our research, right? And what I'm going to present is pretty simple. We modeled the problem with just 2 layers. At the higher level, there is a task assignment on a graph. The states are the nodes where your vehicles are located, as well as the state of charge. And later I'm going to call that capacity. I'll tell you why. So there's a node and state of charge, and the input is what task you have to execute till the end of the day, of the month, and so on, whenever your mission ends. Okay? So imagine all these nodes being your physical location, where you have to do certain experiments, and the graph carrying the energy to go from A to B. Okay, here you have 2 vehicles, the green doing 3, 4, and then we're back to the depot. The blue doing 1, 2, and we're back to the depot. Okay. The lower level is a path planner. Before the node K, the lower H stands for high level. K was an event. So this evolves. At the high level, you evolve an event-based. At low level, you are time-based, usually faster sampling time. The states are your position, velocity, and state of charge. These are the F that I showed you before. Newton, powertrain dynamics, and the input in this, let's assume very simple, you have steering and acceleration. So, how is it done today? Every good engineer will design it in this way, and it is done in this way. You overestimate energy. You overestimate energy on each edge, and you solve a mission plan at high level. Because you have overestimated energy, the low level will be able to deliver that mission. Okay? So, it's as simple as that. It guarantees mission completion. However, inefficiency, it's very inefficient. Inefficiency means that you increase costs. Okay? You have really low utilization of resources. In the transit world, this would mean that these buses are, in the United States, around $1 million a bus. Okay, so your dollars per trip increases. Okay, and your total cost of ownership, it's extremely high. In a case of a mission on another planet, it means that your throughput of experiments goes down, or your cost per experiment is extremely high. So everybody's really interested in increasing this efficiency in a safe way. Okay? Our simple idea is to say, let's explore the iterative nature of this hierarchical system. Use data to update both the high level and the low level control policy. At the high level, you assign the tasks. At the low level, you execute the tasks. So now the notation becomes a bit heavier. By the way, I'll remove the index of each vehicle because then would be other, I need to go to the left here. So it would be the H is for high level, event K, iteration R. This is an episodic iteration. If your bus would be every day, if it's your mission on Mars, would be a sol day. And so this would be the state at event K at the high level of iteration R. So you have inputs, and now the energy on an edge will be at the energy, your best estimate of that energy at iteration R. Okay? Similar for the low level, you're executing a path planner, but most probably you have already seen this I to J motion, okay, node I to node J. So the R will be the state at that iteration at that time step. Okay? So the policy now are at the high level your task assignment. Remember, your task sequence of tasks depends on your best estimate of energy at R at time R at iteration R. At low level, the agents use historical data to update their motion planner. Okay? So, summary, we dynamically update the low level at every time step, the high level at that event, at data at every iteration. So if you want to see a graph, decide to do a video in case it's not clear. You have your agent has to go to NJ, the high level decided the best thing to do is to go to node J. You have an estimate for this node you haven't seen before. You send this to the low level, you execute that. Your predicted state at the high level at the next step now is replaced with the measure state. Because you have data, then you update the energy on these nodes and you repeat the assignment. Possibly deciding to visit to do this task, or maybe you decide that this is not a good idea, you're going to explore some other areas of the graph. Okay? So, I don't have to convince you, this audience, that if you don't do this right, you become invisible, right? This is what you see, the red line here is the number here, in this case, of customer visits. You can think of this being electric Amazon delivery, okay, for instance. You increase your performance, you can deliver more packages to your customers, but at some point you become invisible. You won't be able to finish your job, yet they have to call, and it's called a return to station. They have to pick up somebody to tow the electric vehicle back, okay? So we have been really trying to think about how we ensure feasibility and how we minimize computation for this class of problems. So this was the idea. I'll tell you all the details. Instead, I'll tell you one detail, how to design, which is really the key detail, how we design the low-level controller. And the low-level controller, because of my training, my bias, is an LMPC. It has two classes of states, the capacity states and C, and the motion states key. Okay? So capacity could be state of charge, could be time, could be the volume you have in the back of your Amazon bag, right? These are all integrators dynamics. Your key are all the motion part of it, latent long and velocity and orientation, for instance, okay? The assumption that we need is that the motion, the key, does not depend on capacity, which is a decent assumption, and capacity constraints are actually monotonic. The capacity, the next step is the one previous plus some positive function, okay? So again, if you think about the battery depletion, that's the opposite. You can model, instead of the battery going from 100 to 0, from 0, the opposite, how much from 0 to 100. So here's the idea. It's a learning MPC style. You're going from node I to node J. You have collected a lot of points at the low level. These are your latent long, okay? And the blue, and these are the gray dots. The blue dots are your latest iteration. That's R minus 1. I solve for each point. Now you compute the cost to go. You do this using Bellman principle. You sum the cost in closed loop because you have recorded it until you reach the NJ. You've completed your task. So this is going to be your Q at iteration R. This IJ tells you that it's context dependent, meaning you can be in a certain state by doing another edge. Okay, so that's very important that you carry the cost. And this is your MPC, classical optimization problem. I'm adding one constraint. This is what makes everything work. You land in a state that you've seen before. That's the X bar, in any of the blue dots. Land in any of the blue dots and make sure that the capacity, the predicted capacity over your short horizon is less or equal than the recorded capacity at that dot. So I'm enforcing I require less energy, okay, than a data point that I've already seen and my previous iteration. That's as simple as this. Okay. Now, even if you're short-sighted, because of the integrator dynamics, it turns out that over the whole horizon from I to j, you're actually going to take less or equal energy than you took at the previous iteration. That's really the only key here. People are thinking, well, this looks like a MIP. This is actually it's a nonlinear mixed integer problem because these are a discrete data set, and these are nonlinear dynamics. Yes, it's a nightmare, but this what we do is we lift the nonlinear dynamics. These are quasi-linear dynamics. We take the convex out of the points, and we take again the barycentric approximation, so we solve this IP-opt. It's a large nonlinear optimization problem. It's not too bad, actually, for the class of problem you're looking at. Okay. So then there's MPC. You take the first iteration, you move, you resolve the problem of shifted horizon, and if you impose these two little constraints I told you, then you get that the state over at iteration r over the arc ij consume less capacity than the previous iteration. Okay, so I think this is all really it's really the key part of this presentation part of the presentation. You also, as you execute, you do a better job in path planning from going from I to j, and your computation interactive because you solve small optimization problems. That comes from MPC. Well, key points, of course. The next iteration, you take all your data, you put that in the stored set, the safe set S, and you update your cost to go function again using Bellman inequality. At high level, I just have one slide, that's why I'm here. Hopefully Bartolomeo will give me some smart idea on how to do that. It's a location, it's a graph search. I'm trying to, I have a graph, I want to visit as many nodes I want, and I have edges which are my best estimate of energy at that point in time, okay? So the goal is really to send this vehicle and visit these edges, okay, while you satisfy the mission capacity state, and you improve resource utilization as data is collected, okay? This belongs to the class of capacitated vehicle routing with time windows. I don't know if you're familiar with this. Time windows because especially in the bus case, in the transit case, you have certain time you want to be there at the stop, right? Similarly, if you're, your Amazon, they'll tell you to be there in 2 hours. Also for a space mission, they have certain times they can be there and collect samples. So that's why the talk was about general capacity. We see time as just another integrator added to the energy. We could do LMPC for graph search. We have coded it up. It works okay. But again, we don't know how to do this efficiently. Okay. As I mentioned before, if we combine the low-level MPC with any high-level optimization, you end up with. Oh, by the way, this is how the scheme. Sorry, I'm going way too far. This schema works. You initialize with some part at the low level, even if this is done. Even if you have never seen that before, maybe you stay away from obstacle and you go very slow. That's usually done space missions, right? The high level, you're going to say that you're going to overestimate energy. Okay, that's how you start the system. Then at each iteration, you use data, you update the energy consumption, and you do a task assignment at high level, send this to the low level, which does an LMPC, trying to improve the path planning and energy consumption, path planning performance and energy consumption on that task. Okay? If you do this as I designed, as I showed you, then you will see that you will always be feasible at every iteration, and your performance will improve between iterations. Okay? What is the proof? It's simple. The proof relies on the point that I just showed you, that at low level, the policy is designed to decrease energy consumption and satisfy time bounds. Because you are starting with an overestimate, you will always do better. It's as simple as that. Okay, so because your design, again, because of one, that energy consumption decreases, because you have integrator dynamics, and because you are updating the energy consumption, then the higher level will always have a task that is feasible and better in terms of utilization. Okay? I'm going to skip this slide, go to the simulation example. This is a 6-stage system. You have motion, and one vehicle, two states, state of charge and time. The motion is nonlinear. The state of charge and time are integral dynamics. You see they are the state of charge is a function of what is your speed, okay? And you start with iteration 0 saying that 1 is your depot. You can visit 6 and 7, and you have some overestimates on all the energy on the graph, okay? As you keep iterating and collecting data, the vehicles the location that you visit, okay, increases, your performance increases, okay? If you focus only on one edge, you're gonna see the edge 6, 2 here, which remember was not seen before. You had an initial guess on the energy, which is this one here, the energy is here, 20, okay? Energy consumption was 20% of state of charge, and you had the initial guess on a plan, but you've never executed it. It's an overestimate. When you go to the next iteration and you do try to allocate 6-2, you'll see the path slightly change. It's a little bit better in terms of performance from a top view. This is an XY motion to go from here to here. But your speed increases. You're doing this at a faster rate, and you're also decreasing energy consumption as well as the time to get there. Okay? This is all what I want to show you. I've been interested in this class of problem because I think it's because it will be important to solve now that we electrify our fleet. I'm on industrial leave, and for the past 5 years we have been building at Whitesense this platform that does this. It's very complicated, but it's just not simple. We take data from vehicles. These are usually you can connect with vehicles through a data hub. And these vehicles are either cars, vans, passenger vehicles, delivery vehicles, or transit. We take data from weather, traffic, elevation maps, so we can contextualize this data. And that's what this model on the left-hand side does. On the right-hand side, you have the model library. These are all the models of powertrain and motion that I've showed you in the third slide. In the middle, there is this learning engine, and there is a learning model database where you learn per vehicle, per powertrain, what is its behavior has been based on historical data. Then you do contextualized predictions. Today, given this weather, the driver is going to turn on their conditioning. Given this traffic, this is going to be the state of charge, okay? Depletion. And here is where you get your optimization. The yellow is the high-level emission planning. That's what I talked about today, right? I'm on industrial leave. I've been working with people at Whitesense for now 5 years, but full-time for the past year and a half. And really the output is which electric vehicle should do which job, when should it charge, where should it charge, and for how long it should charge. Okay? Simple as that. It's, the reason it's really simple. You either solve this problem, you will not see electric vehicles around. Whether it's Whitesense or not, people will need to build this platform simply because because it takes time to charge. Unless you change batteries, chemists, and you do batteries that can solve, that you basically replace, you can have the same way of operate a fuel car, meaning you can charge everywhere and it takes a few minutes, then you need this system. And if we are deployed all across the United States with major electric bus fleets. If you use a major road assistance brand in the United States, and when you have electric vehicles, they will pick you up. These are recommended by this engine. People that rent electric vehicles to Uber drivers, right? For instance, they need this type of platform, and so on. So I'm very excited. Maybe this is again in the future. I'll tell you more about this if if electrification happens. The other scenarios that we go back to internal combustion engines. Hopefully that's not the case. Thank you for your attention. I want to tell you what we are doing in the lab with learning for cars, and I'll tell you about this cool research on hierarchical optimization. I'm here for taking any questions.